Dave Maiullo here, and welcome to our virtual edition of That Physics Show. We're so glad you're able to join us wherever you are, all right? Hey, before I get started, with all this great equipment behind me to show you the world of physics, show you all the physics that you probably already knew already, show you those laws and rules that we have in physics. Before we get to all of that, let's just talk about physics for just a couple seconds, right? Just a couple seconds. You know, physics has a lot of laws, has a lot of rules, as we just said. Those laws and rules we have in physics, kind of like the Supreme Court of all the other sciences, really. The laws and rules in physics make up chemistry, biology, engineering, medicine. They have to follow the laws and rules we're going to see right here on our stage today. And, you know, this is a bit of an off-Broadway show, right? So we really do have a bit of a theme all through our show. The theme to our show is really energy. Energy, that's the word. And it means this. I'm never really going to get rid of that energy. I'm just going to move that energy around. And in moving it around, we can do things. In fact, I can make sound with energy, or we can make light with energy. Because the very first thing we're going to do here on our stage today is talk about Isaac Newton's 3 laws of motion. There are 3 of them. And they really concern, more than anything else, how mass and force interact. And we're going to see all 3. And that first law of motion is known as the law of inertia. That's the word, and that's what you want to remember. And actually, here's what it means. It means that this mass, this plate, won't do anything at all, will not move at all. No motion unless a force acts on it. But once the plate goes into motion, it keeps moving till another force acts on it. Hey, that's the word, and that's exactly what you saw right there. Now, you see we have a tablecloth here, and we got some flowers, and there's even a candle here, and I bet you didn't know this. There's actually romance in physics, too, so I'm going to light that candle up. Now, you see all those objects on our tablecloth? Remember, inertia means objects don't move unless a force acts on them. So I'm going to take the tablecloth, and I'm going to move it very slowly. And you're going to note that all those objects move directly towards me. You saw that. What was the force on all those objects? It was friction, right? There's a rubbing between the tablecloth and the object, so they move, right? Hey, friction's an important force. There's no walking, there's no driving unless we have friction, right? We know that on an icy day. But hey, here's what I can do. If I take this tablecloth and I move it very, very, very quickly, that actually overcomes the static force of friction on all those objects. That means they really shouldn't move at all by pulling the tablecloth out from underneath. You think it's going to work? I say we try, because how do you really learn in life? You do the experiment. So let's do the experiment. 3, 2, 1, and they stay right there just like that. So that's what we have with that law of inertia, the first law of motion, but there are 3 of them. And the second one may actually be my favorite. The second law of motion tells me this, that every force, what's that? That's a hammer. Every force is equal to mass times acceleration. Wow, you heard me hit that piece of wood? You know a hammer provides a force. That's exactly what these do, right? You ever hit yourself in the thumb? You know what hammers do. So, force is equal to mass times acceleration. Oh my goodness, a physics equation. That makes it really scary? No. It really just models exactly what we see in life. Let's break it down. What do I have right here? That's a sponge. That's our light mass. Piece of wood, that's our medium mass. And right here is a heavy, massive lead brick. So if I have 3 different masses and I take this force, this hammer, and apply it equally to each one of these masses, what does that equation say we're going to see? Different accelerations. But again, how do you learn in life? You do the experiment. So let's do the experiment right here in front of you, all right? So force, mass, and acceleration. Force, mass, and acceleration. Force, mass, and... That one's not moving far, is it? You saw how the sponge, the light mass, flew out and accelerated very fast. How the piece of wood just kind of flopped off the table. Less mass on the sponge, even less, you know, a little more mass on that piece of wood, so it didn't accelerate as much. But this big lead brick is hardly accelerated at all. In fact, if I was to take this force, this hammer, and bring it down on my hand like this, it's the shortest show you've probably ever seen, because I'd have to go off to the hospital, right? Instead, I take that big lead brick, I put it right here on my hand like this. It really doesn't matter how much force I now apply to that lead brick with this hammer. It really will not accelerate into my hand at all. So I can take this hammer, this force, hit the lead brick really hard on my hand, and I feel none of the force of the hammer blow. Doesn't affect me at all. But there is a third law of motion. And the third law of motion is what? Every action has an equal and opposite reaction. I can take my two hands. I can press them together really hard with lots of force. But you know, there's no motion there, right? Nothing's actually moving, just a lot of force both ways. And here, Ryan has brought out this really, really pretty red cart. You know what I can do to that pretty red cart? I can push on the surface really hard. But the cart just pushes equally back on me, holding me up. Force down, force up. That's what we have. But this law, every action gives us an equal and opposite reaction, does give us motion. And when does that happen? Well, what's in my hand right here? That's a balloon. What is it now? It's a balloon filled with air. And have you ever done this experiment? Probably, right? I'm going to take the balloon and I'm going to let it go. The balloon's going to go in one direction, but what's the air going to do? It's going to go the other way, which is why you get motion with this law. Every action in equal and opposite reaction. 3, 2, 1, and off it goes. But that's not so exciting. Let's try the exact same experiment with this. What's this? This is a fire extinguisher, right? Filled with lots and lots of CO2 under very, very high pressure. Lots and lots of force. I'm going to take all the force in this fire extinguisher, and I'm going to go ahead and I'm going to hit that sail right there with all that force. Now, as you're watching, I want you to tell me, what direction does my cart then go in when I do this experiment? Hey, you don't have to, I won't know what you're thinking, but think to yourself. But let's do a physics survey. Who thinks I'm headed that way? Who thinks I'm headed that way? Who thinks I'm headed this way? Who thinks I'm going, well, sooner or later. Not today, I hope. By the way, this is going to be an extremely loud noise, so let's see what we get here. And it's just like a grenade. You actually pull the pin. There's that much force in here. So let's do our experiment, all right? 3, 2, 1. Which way did I go? Nowhere. The only thing that happens is your butt gets really cold because it goes right down your shorts. Now, why? You saw and heard how much force I put on that sail, but there's no actual motion. But of course not. You don't push on yourself and go into motion. That's not how this law and rule works, right? In fact, what do we have to do? Well, this is why we have Ryan. Because Ryan is now going to stand directly behind me, sound headphones on, with that sail. And all the force of this fire extinguisher is going to come out and hit that sail now, but it's not attached to that cart anymore. What direction is this cart now going to go in? That way. That's obvious. But let me ask you this. Does Ryan have to be behind me here with that sail for me to go forward? And the answer is no. Right? There's nobody in outer space standing behind rockets. That's a lousy job to have. But we gave this job to Ryan because we want you to see how much force is on me and him as we do our experiment, okay? So you can see us both for a second, but let's see some rocket motion in action. 3, 2, 1. This right here in this container is water. Does anybody know what that is? Well, that's just regular soda, right? Regular Pepsi. Does anybody know what that is? Well, that's Diet Pepsi. And I bet most of you have picked up one of these or maybe even picked up one of these. But here's my question to you. You know what water is. You know what soda is. Does this can of regular soda sink or float in the water bath? Well, what do we do to find out? Let's do the experiment. So I'm going to put it right here in that water bath. Let it go. You'll note it goes right to the bottom, right? I don't know how many predicted that, but that's exactly what happened. Right here, we have a can of diet soda. Does this sink or float in the water? What do you think? Well, I say you try it at home. No, 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 I'm going to do it right here. Let's do that experiment right here. I'm going to go ahead and put it in a water bath, and actually, it floats. Now, why would that be? Seems kind of surprising, right? Because they give you the same amount of soda. They give you the same amount of bubbles. So why do they have a different density? Because that's why things sink or float. It's the density relationship. Well, this soda down here is sweetened with sugar. And that sugar soda, if you take that sugar out, there's a good almost an inch or inch and a half of sugar inside that can of soda. That's what you're drinking. Yum, yum, yum. It really has a high density in comparison to this soda, which is sweetened with something we call NutraSweet. You just need a little bit of that really powerful chemical to make it as sweet as all that sugar. So this is more dense. This is less dense, as you can see. But has anybody here ever been in a swimming pool? And I bet the answer is yes. And anybody watching, have you actually been in our ocean? And again, I bet the answer is yes. And where do you feel more of a buoyant force lifting you up? Well, in the ocean. Why? What's in the ocean? Salt, sharks, toilet paper, lots of stuff. So if I take some salt and I pour it in a water bath, we see that that brings that soda right to the surface, just like so, just like that. Because now it changed the density of the water bath, and in sinking and floating, it's all about the relationship of density. That's exactly what we've done. Make the water bath more dense, it comes to the surface. But what floats in our air? Balloons, right? You ever have a birthday? What do they give you? They give you a helium balloon, right? And what I have right here is a helium balloon. You know what I'm going to do to that helium balloon? I'm going to pop it. I am. But I'll explain to you a little of the fun facts about helium, because when I pop that helium balloon, here's what's going to happen to the helium. The helium is going to leave this area right here. It's going to leave this building. It's going to go all the way up to the top of our atmosphere and then leave the Earth. It turns out that helium isn't held to the Earth by Earth's gravity. Earth's gravity is not strong enough, so any helium in our air winds up in outer space. And if that's all true, and it is, where did human beings actually first see helium? Well, it turns out it was also outer space. It was actually on the sun. In fact, helium is named after the sun. Helium, helios, that's why it's called that. It's named after the sun. We saw these burning yellow lines, these yellow-colored lines, and that told us there was a gas on the sun that we didn't know about. And then we looked here on Earth for that same gas. Where do we get our helium from now? And don't say the party store. It turns out that it comes from underground. When they pull gas from underground, a whole lot of helium comes with it. But we waste most of it. In fact, most helium winds up in outer space that we pull out of ground. In fact, we actually have a shortage of helium right now. Pretty dangerous shortage, because we use helium in quite a few things. But let's send more out to outer space and say goodbye to a little bit of helium, right? Let's see what happens when we light this balloon. 3, 2, 1, pops it. But we have a whole nother gas right here that floats a whole lot better than helium. And we're never, ever, 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 ever going to run out of this gas. So with helium being in a shortage, why don't they give you hydrogen balloons? I'll show you. So I'm now going to light this balloon, and you're going to see the difference between helium and hydrogen. For this, we'll turn the lights out. Let's see if you can keep your eyes on this hydrogen balloon. 3, 2, 1. An amazing sight, isn't it? Now, oh, thank you, Michelle. Here's what I got. What's this right here? This is a garbage can, right? It's a garbage can. What's it have on one side? It's got a hole. What do I have on the other side? I got some rubber right here. So more than anything else, this is like a big drum, right? And I can take this, I'm going to hit the bottom, but you don't actually see anything happen there. So you don't really know that anything's happening when I do that. You know, in physics, and I actually think in science and life, you want proof of things, right? You want to see what something's doing before you believe what someone tells you, right? Don't just believe what people say. Look for some proof. So Michelle, she's got a candle, right? And a lot of times in science, we see action at a distance. We don't really see what's going on, but we see what the thing does, right? So let's see what we can do with this, because with my garbage can, I can, let's see, blow the candle out. So you can see that this is actually doing something. But you still didn't see exactly what's happening with our garbage can. And in physics and in science, what we like to do more than anything else is see exactly what's going on. So let's see that, because what I have right here is some theatrical fog. Now, theatrical fog is just glycerin that we heat up. It becomes a fog. They put glycerin in all your food. They just don't tell you. So no, we're not worried about this stuff. but it will show us exactly what's happening every time I hit the bottom of this garbage can. And this to me is one of the reasons why science is so much fun. Because what do we got? We got that smoke ring coming right out at you, right? And look how simple this is to make. And I dare you to go home and build one of those. That's what we have coming out of here all the time. But you didn't know it till we put the fog inside. And that's the fun part of science, seeing exactly what happens. Now, Ryan's got another object for me over here. What's that? That's a square. What's the shape again? That's a circle. So let's take our square. Thank you, Ryan. I'm going to take that square. I'm going to put it right here on the front of our garbage can. You here watching, tell me, tell your friends, what are we going to see next? Circles? Squircles. What kind of shape will come from our garbage can? I say we now do this experiment again. And for this, I'm going to add a little more fog. Let's put a little more fog in here. Good deal. So did you predict? Because that's what you have to do in science. You want to come up with an idea. Come up with a theory. What will we see coming out of here now? Squares or circles? Well, let's do the experiment. I do it, and you'll note it's actually still that smoke ring, that smoke circle. Now, why is it not a smoke square? Well, smoke squares are like unicorns. You want them to be real, but they don't really exist. The stability of our smoke ring is very different. You can't get that same stability in a smoke square. It doesn't happen, okay? It just won't exist. Won't stay stable for long enough to propagate across. So that's exactly what we have with air. But, you know, we've been playing in the lab a little bit. And Ryan here has a whole nother shape, the ellipse. What Ryan is now going to do is take the square away, and I'm going to take this ellipse, I'm going to put it right here on the front of the garbage can. And it turns out that something rather special happens when we use the ellipse. In fact, one of the things we just discovered in physics, cosmology, is that gravitation waves move across our universe. Well, it turns out when I put an ellipse on here, these gravitation waves look pretty much like what you're going to see right here. An oscillating ellipse coming right towards you, back and forth, as that comes out of there. And that shows you you can actually do modern cosmology with a garbage can. How much fun is that? See if you can answer this question. How big is that sound? It's actually a pretty good question, right? Because we don't really know. We know how loud a sound is, how low a sound is. We measure sound through decibels, but we don't measure the size of sound usually as human beings. Why not? Because we don't see sound as human beings, right? You don't really know how large it is because that's not how we measure it with our ears. We basically have to see something to know how large it is, right? So we know an elephant is really large because we can see the elephant. We know a mouse is really small because we can see the mouse. And you don't see this sound. Or here in our show, we're going to show you exactly how large this is. And how am I going to do that? Well, I'm going to use fire, of course, and you knew that already. Just like that. I'm going to make this a nice even flame, just like this, right across the top of our tube. And now what I'm going to do is I'm going to put that sound energy back inside the tube. And when I do that, we see the size of that sound. That's exactly how big this sound is. And it looks just like a rope slinky, doesn't it? As a wave motion going up and down and up and down and up and down. If you could see that wave of sound coming to your ears right now, you would see that. And it's beautiful, right? And it's just a wave motion and kind of fun to see. But here's what we can do. I can change the tone of the sound. I can go higher in pitch, right? And when I do that, I want to ask you, what happens to the size of our sound? Well, I say we do the experiment. Predict to yourself what's going to happen and then see it. Higher sound, smaller wave. And I can go lower in pitch. And when I go lower, you see we have a bigger wave, right like that. So the low waves in sound, they're big waves. The high frequency sounds are small waves, as you can tell with our flame tube that we have right here in front of you. All right? But this is just one tone we're putting in our tube. And what might be fun is instead of using one tone, is to use a song. And I know you all have your favorite songs. I realize that. And you know what? I'm not going to play any one of them. Instead, I'm going to play a song that you might hear if you've ever been in a wedding. Let's see if you can hear the song and see the dancing waves of a song in our flame tube. Here you go. And you can see that the tube reacts by giving us that large wave. And now all these different ones, the dancing waves of a song in the flame tube. And that's exactly what we have in this. It's a beautiful example of the waves that you can have inside and how you can see all those different waves. In physics and in science, when we discuss temperature, we're really discussing energy. We really are. We think of high temperature as high energy, low temperature as low energy, right? We think of a thermometer as an energy scale. And what I have right here in my hand, well, this is nitrogen. But this is nitrogen at minus 300 degrees. So it becomes a liquid at minus 300 degrees. And you can see it's kind of steaming out the top. And as I pour it out, it hits the floor and expands quite a bit. It turns out the nitrogen expands to 700 times its size from a liquid to a gas. And like we say, this is low temperature, but again, low energy. So anything I put in here loses its what? Its energy. So that's what we want to see right now. And the most common question I get from people when I do shows, and I do a lot of shows, they all say to me, hey, what happens when you put your hand in a liquid nitrogen? Well, I'm not going to do that one. Instead, I'm going to do this one. What's this? This is a hot dog. And am I a hot dog or what? Oh, yeah. And this is a room temperature hot dog, right? It's not frozen or anything. About the same temperature as me. If I press on a hot dog, it just crushes. And that's exactly what would happen to my body, my hand, if I pressed on it hard enough, it just crush. I'm meat just like the hot dog, so it would crush. So if I take a hot dog and I leave it in the liquid nitrogen for a period of time, this is exactly what happens to the hot dog. This is a minus 300 degree hot dog, all right? You can see the steam coming off the hot dog, but you can also note that this is exactly what would happen to my hand. Smashes and crushes just like that. I could do the experiment twice. I got two hands. I couldn't do it again. So people see me use this stuff in shows, and usually after a show, a child will come up to me and say, hey, where can I buy myself some liquid nitrogen? I'd love to have a little bit of fun with this stuff too. No, you don't want to play with this stuff. It's actually really dangerous. Well, a lot of people die every year by playing with liquid nitrogen. What do they do to die? They drink it. A really bad thing to do. Because what happens is it expands inside your body 700 times the size, your insides explode. A nasty way to go. You can also get a very severe burn by the liquid nitrogen. Worst burn I ever had in my entire life was liquid nitrogen. And how did I get it? Got inside the glove I was wearing, held it against my skin for 10 seconds as I pulled the glove off. Took 2 months for that burn to heal. But I can do this. I can pour the liquid nitrogen right over my hand like that. You notice that the liquid nitrogen just rides over the warm air on my hand. Never actually touched me, so I didn't get a burn. But what happens if I pour it into my hand like this? Worst burn in my entire life. So you got to be very careful with liquid nitrogen. Well, we do want to see what it can do. So let's take a look at what it can do to some everyday things. What do we have right here? Well, that's a banana. And what's that right there? Well, that happens to be a banana split. And what do we have right here? Well, these are flowers. And don't we all love flowers? But that's a room temperature flower, right? But let's take that flower and put it in a liquid nitrogen. Now, what am I doing to the flower by putting it in a liquid nitrogen? I'm taking the energy out of the flower. And there's nowhere on Earth that's really the temperature of liquid nitrogen except the lab. Right? The coldest place in Antarctica is like minus 190. So there's no place you can do this except the lab. We do this to everything. We want to know what happens to these objects when we make them this temperature. How does it act? We take the energy out. How does it act? So we take the flour out. We see it looks just like before, only now that flour breaks just like glass, just like glass. Hey, this will tell you a lot about liquid nitrogen. What kind of balloon is that? Don't say hydrogen, a helium balloon. I'm going to take that helium balloon. I'm now going to roll it into liquid nitrogen. And as I do that, what happens to the balloon? Well, I'm slowing the helium down in the balloon. So the balloon gets smaller. It's no longer pressing on the inside with such force. And as the balloon gets smaller, it's actually more dense. So now it's a dense helium balloon that no longer floats. But I can take the balloon out, let it hit the floor like that. You'll note that the balloon starts to re-expand. And as it re-expands, it becomes less and less dense until finally the balloon can come up off the floor, re-expand, and come right back up. Helium balloon lives again. There you go. Everybody likes that. Now, this will also show you a lot about liquid nitrogen, because remember, it goes 1 to 700 times its size from a liquid to a gas. So if I take it, pour it in a tube like this, you can see that as the steam pours out the top of that tube, you get that expansion coming out the tube. There's a lot of energy in that expansion too. In fact, I can use that expansion right now and that energy, try to cork it, it becomes a liquid nitrogen cannon. Watch out, Cap. We have right here the beds of nails. You can see these nails on your screen right now, and they're actually nice and sharp. Remember, it's all about Newton seeing that apple fall. Or here's an apple. Gravity pulled it down, hit the nails, but you can see all those holes in our apple. Those nails on our bed of nails are very, very, very sharp. But here's our experiment. We're going to take that bed of nails. We're going to put it right down here on our floor, right down there. I'm going to take my body and lay it across that bed of nails. We then have a second bed of nails. We're going to put the nails down on my body. And then I'm going to take Michelle, who's going to stand on me. And I'm going to be a Dave sandwich in between the beds of nails. Will I be okay? Well, I say we do the experiment and find out. Let's find out. So down here I go, on our bed of nails. And every bed needs a blanket. Mine just happens to be more nails. Right down there on my body. Yes. Oh, good. Now, I'm a Dave sandwich in between two beds of nails. And Michelle is going to add her mass to our beds of nails. And notice, I'm just fine. I'm perfectly okay. It doesn't really matter that Michelle is standing on me like this. I feel just great. No, I'm kidding. But you can get on down. Thank you, Michelle. At home, a big round of applause for Michelle. Now, we're going to take that off. And remember, our saying is in our show, that physics show, it's not magic, it's physics. So let's see what we mean by that. Because that looked suspiciously like a magic trick. But think about it this way. I weigh 200 pounds. If I lied down on a bed of nails with one nail, that'd be 200 pounds of force on the one nail. More than enough to pop that nail right through my body and kill me. Let's say my bed of nails had 10 nails. Well, there's 20 pounds of force on every one of those nails. More than enough to go right through my body and kill me. Let's say my bed of nails had 100 nails. 2 pounds of force on each nail. That hurts a little bit, but it won't go through human skin. You actually need about 12 pounds of force on a nail to go through human skin. Hey, I'm a scientist. I did the experiment. It was a bad day, but I can't help myself. So this is something really similar to me. Thin skin and filled with hot air, just a balloon. And this here is a whole lot of nails. Will this balloon bust on all those nails? I'd like you to predict, because it doesn't. There's not enough force in any one balloon, any one nail to go through the skin of the balloon. Here we have one with half as many nails, doubling the force in every one of those nails. Will the balloon bust this time? I say we find out. Do the experiment. Because, no, when I'm pressing, it still doesn't bust. Here you have a bed of nails with half as many again, doubling the force one more time. Will it bust this time? Well, it's our last one. So of course, it's gonna break. Just like that, how I would pop on a bed of nails without many nails. Now for our last demonstration, we're gonna ask Ryan to go ahead and lie down on our bed of nails. Thank you, Ryan. He's quite comfy, right? And now Michelle's gonna bring over a couple objects. Thank you, Michelle. The first we have is our sign, right? That physics show. And if you like what you see in our video, please come and see us on our off-Broadway show when we're back and running like everything else on Broadway. And it looks just like a guillotine, doesn't it? So we're gonna put it right here on Ryan's neck, just like that guillotine. Next, we have a cinder block. And we're gonna place this cinder block right on Ryan's rock hard abs. Now, the last part of our experiment is the sledgehammer. So here's our experiment. Bed of nails, Ryan, brick, sledgehammer. When I break the brick, does Ryan live? What do we got to do in life? You got to do the experiment. So 3, 2, 1, bust the brick, and Ryan is perfectly fine. Dave Maiullo here signing off. Thanks again for attending.
Hope you all enjoyed. Any questions from anyone? What kind of demonstrations can students do at home? Well, certainly density experiments are pretty easy to do. Water is always available, right? And usually you just need some kind of place to put it in, and then you can try to sink and float many different objects. Just be safe, of course. You don't want to grab anything that's alive and you're just going to drown. At the same time, you want to actually, play with different size things, play with different things that feel different. Rock, you got a sponge, you got lots of different stuff inside the house, and try to surprise yourself with what may sink or float. Certainly you can do experiments with force and pushing on things and seeing how things react to different forces. Again, be careful. You can't do this in any way that's going to lead to violence, of course, but you want to, take your time. Always have parental supervision. Make sure they know what you're up to so that you're not getting in any trouble by doing something. And please don't use a fire extinguisher to push you around. For one thing, it's not going to work. The way you set it up, I had to modify those fire extinguishers. Plus, you're going to get in a lot of trouble. So don't use a fire extinguisher for any reason at all at home except to put out a fire, okay? Well, really, touching that hot dog when it's really cold, really the whole point is you saw me actually moving it around quite a bit when I had it in my hands. That's because I don't want it to stay in one spot for any amount of time. By not having it stay in one spot for any amount of time, I can actually have it move very safely on my skin. If it was to stay in one spot on my hand, that's when I'd get the burn. But I'm kind of tossing it around quite a bit, and that allows me to keep it in my hand, just not in one spot for any amount of time. I found pretty quickly that I'm safer, without the gloves, just because that's when I got burnt, that liquid nitrogen got inside the glove. So kind of learned how to use the liquid nitrogen without the gloves on, and it actually works pretty nice. You want to protect your eyes, of course, but in every other way, I'm just fine. Favorite demonstration is it's an odd question because I have so many. So look, favorite demonstration, I love all parts of physics. I love the physics that we have when it comes to, forces and the force laws. And so fire extinguisher cart, how can you go wrong with that? Certainly the flame tube, AKA Rubens tube, is something that's fantastic to see. First time I saw that, I was blown away. And every time I show it to people, they love it too. So that's one of my favorites. I can't say I have a specific favorite. Certainly I've probably laid my body down on beds of nails over 1,000 or so times. I've done so many demonstration shows, including all the ones for that physics show. So, that's one of the ones that's kind of crowd pleasing and also kind of fantastic. So, it's obviously one of my favorites, but you know, they're all good. Physics is fun no matter what part of physics you're doing. Most fun. Biggest fail, you know, the way I see science, you never really fail. You just kind of have to redo the experiment so that it works. And you learn so much by doing the experiment and, you know, quote unquote, failing. You actually learn by when things go wrong. Biggest fail, well, I've been in front of a lot of people when just demonstrations didn't work. And you know what? So what? You know, if you just roll with it, keep moving along, don't stress over it, the show can just be fine anyway. That's the way I see it. I'm just happy to be part of this Empire State Maker Faire. I always find the people as part of the Maker Faire, they're so enthusiastic about science. They're so much fun. And hey, look, anybody who's enthusiastic about science, that's the people I want to hang with. So so it's great to be part of this effort and great to be part of the Maker Faire. I just wish we could be live and be in some place where everybody could kind of look at everything, but hopefully that'll happen soon. Hi, Eileen.
Hello, hello. I figured I'd jump on in.
Thank you so much.
As someone who is also enthusiastic about science.
I know you are.
Thank you so much for your presentation. That was awesome. And boy, do I miss that physics show.
I know. Well, you were a big part of that effort.
Certainly. I was one of the assistants for that physics show. And then I soon became one of the demonstrators of that chemistry show. And now I'm the executive director of Science Theater Company, which is the new nonprofit that's going to be doing all of these shows. So if you want to follow us, you can follow us on social media or go to our website, and there's going to be all kinds of new science shows. We're posting videos of that physics show as well as some other science demonstrations. So if you want to see what else Dave and I are up to, you can follow us along right there. But we are still doing our science, even though we can't do it live off Broadway at the particular moment.
Exactly right. Exactly right.
So I've got another question for you, Dave.
Sure.
So I'm curious, are there any demonstrations that you've really wanted to be able to do that you've never been able to?
Well, I've done some demonstrations in the classroom, like boiling water with a vacuum and things like that, you know, that I haven't done on the stage yet. You only have, you know, our show is about 90 minutes long or so. And so you only have a limited amount of time. But certainly there's a bunch of different ones, shrinking peeps down with a vacuum. And then, well, first you get them to expand by pulling vacuum, and then you kind of let the air back in and they shrink down to just a puddle of goo. That's always a good time, you know. Who doesn't like shrinking a peep? But, you know, there's lots of different things that we can do on a show. And, you know, if we ever get the nonprofit up and running and back to the stage, I would, you know, probably add some demonstrations we haven't done before.
Oh, I can't wait.
I can't wait either.
Awesome. Well, I can tell you one of my favorite demonstrations from especially what we just watched. I love that flame tube. Long through flames. That is so cool.
And to get people to see the size of the waves just through that, so that they finally get a physical sense of what they're thinking about with sound. I mean, just the education behind that, whether you're 5 years old or, you know, 75 years old, it doesn't matter. All of a sudden you have this idea, and that's kind of what we're all about, you know, just showing people these things that are all around them all the time.
Yeah,
So
I know for me it's so cool because, you know, I obviously learned physics from a textbook, and there was so much of it that I didn't understand. And then I started working on the show, and all of a sudden things made sense again. Like there's one that didn't make it into the 30-minute cut, but we do a demonstration with the slinky to show wave motion. And I saw that for the first time, and I was like, I spent a year trying to figure out what that was. And you showed me the slinky, and I get it immediately.
Well, you can see why my day job of doing these demonstrations for the classes at Rutgers University, they really enjoy the demonstrations. And actually, they always tell me in feedback that that's the way they kind of can hang something on that physical law, you know. And it really brings it home. And that's the whole point of it, a good demonstration.
It's so
Especially
helpful.
when it works.
So exciting when you do things like put yourself between beds of nails or
Right.
flying on a
Sometimes I
private
think that's, a little too fantastic because the kids always think I'm going to get hurt. And I don't want them to think I'm going to get hurt. I just want them to see that, what the whole idea is behind that. So I don't want to make anybody afraid for me, but at the same time, it's fun.
Absolutely. And one cool thing that, you didn't get to see in this video, but when we were able to do it live, we were actually able to take volunteers from the audience to be the people who would stand on top of Dave on those beds of nails. So not only were they seeing the demonstration, they actually got to be a part of it.
That's exactly right. And it was fun. Sometimes when we didn't pick on somebody, it didn't work very well because they got very upset. But we just told them to come back.
Yeah. Sometimes little kids would be so worried.
One of my favorite things is I got my mom to stand on me for the last show we did in 1985, I believe it was, when we were first taking the show. And she actually came on stage and stood on me. So that was actually a lot of fun.
That is awesome.
It doesn't like their mom standing on them.
Oh, geez. Well, that was a lot of fun. I think we are just about to come up on our time, but I want to give everyone an opportunity. If anyone has any final questions to pose, we have about 3 minutes left. So go ahead and post in the Q&A section if there's anything that Dave hasn't answered yet. And if nobody has any final questions, Dave, I know you have a question for everybody.
I do?
You always do. I can ask you. The question Dave always asks everyone, why is the sky blue?
That's exactly what I ask. That's right. No matter who I'm with, I always ask that one. And you know what? I get some crazy answers. But you know what? We're seeing that sky all our lives. And so as a scientist, what you want to think like in life is as a scientist. So next time you look at that blue sky, ask yourself that question and then answer it. Find out why, and don't just Google it. Actually learn it. And that's what life, and that's what science is really all about. Understand the things you're always being part of and all the things you're observing. And thank you, Eileen, for all your time here too.
Oh, absolutely. And thank you, Dave. That was so awesome. And that's what we want to leave you all with is go out there, be a scientist, and learn everything for yourself. Get really curious about the world.
And when we're back on off-Broadway, please come and see us.
Yes, absolutely. Thank you so much for watching, everyone.
Thank you. Have a great day.
Bye.